Most languages that provide polymorphism provide some kind of type argument inference, because without it, you basically have to write the same thing twice in your program. If you've worked with an older version of Java, then you know exactly what I'm talking about. You have to write types all over the place for your generics. In Splate, inference means that we can write code like the identity function on the top here and look at that code as the programmers using the language. But what Splate sees is this elaborated code at the bottom. Internally, Splate knows that the identity function has a for all type, but as users, we don't need to worry about the for all. And going along with that, Splate will fill in the types of the applications. Let's see how this works. First, type applications are relatively easy. When we've got an application of a function to an argument, that argument value needs to have a type. If it doesn't type check, then there's no type for the overall application. This means that our type checker can first type check the function, type check the argument, then use the argument's type to supply a type for the application. With that, we're all set. Inferring the typed application is obvious since we can get that type from the argument. Now, how about for a function? How can we infer that a little fun should have a big fun on the outside? The answer here is to relax type validity for a moment and then work backwards. First, type check the function. And then when we see that this identity function will work out and it's got a type with a variable inside, then introduce a big fun to bind that variable. That strategy will normally work, but there are some constraints here. Consider a self-application. Does this expression have a type? Well, it didn't have a type before, but it can have a type now if we use just the right type applications. The key here at the bottom is that x has a for all type, and we instantiate it in two different ways at the applications. First, the x that's acting as a function gets instantiated with an arrow type, and second, the x that's acting as an argument gets instantiated with a type that matches the left-hand side of that arrow. This is really cool that we can now type this expression. Before, it was impossible to infer a type for this because the right types just didn't exist in our language without polymorphism. But we still have a problem. It's now impossible to decidably infer a type for an arbitrary expression. If we want inference to be able to introduce for all types anywhere that there's a type hole, for example, the argument x to this function here, then it turns out that in general, we can't be sure whether inference will succeed or fail on a given expression. It's an undecidable problem. Figuring out where to put for all types and which for all types to use is very hard. Luckily, there's a restriction that we can adopt which makes inference decidable and turns out to work very nicely in practice. That restriction is called let-based polymorphism. We will only infer a polymorphic type and insert that big fun for the right-hand side of a let or a letrec, and nowhere else. And so if we have a let that introduces the identity function, we can infer a for all type for the question mark here. The for all type describes what's on the right-hand side of the let. Something that doesn't work with the constraint is filling in a type for our self-application. Since this type hole is not associated with a let binding, it is not allowed to pick up a for all type. We can try to infer some other type, a non-polymorphic type here, but for self-application, that's not going to work out. So this is not a well-typed program. Since this constraint gives special treatment to let and letrec, it means that these both have to be core forms now. We can no longer encode let as a function application. Another thing to point out is that when we go to implement this, the variables that we'll introduce inside of our for alls can only be new type variables. They can't be bound in earlier parts of the program. So that's let-based polymorphism, and this is a typical way to get for all types and inference in a language. With all this together, we can write Mo code like you see down below. We've got our list of types declares a variable alpha. We can infer a type for our recursive length function. And furthermore, we can infer all those pesky type applications when we go to apply length. And furthermore, not only is this a practical typing and inference scheme for Mo, if we put this all together, it's got essentially the same power as the whole Splate type system. So we've got a type checker that doesn't require you to write too many types, and it can catch all sorts of bugs in programs.